Just a brief outline of today's presentation. I'm going to start off by giving a brief introduction on the Short Span Steel Bridge Alliance, just to make sure everybody's aware of our background and what it is that we've been working on. And then I'll get into the meat of the presentation, which is on the development of a series of standard designs for short span steel bridges. We'll talk about the design parameters and some weight comparisons and some development of these solutions for you. And then I want to talk about eSPAN140, which is the means by which you would access these standards. And I'll go through an example project to show you how easy it is to obtain a steel solution for a short span bridge. Finally, I'll talk about some case studies and some economic assessments on short span bridges. It's fairly related to the topic I'll be discussing today, but I'm not going to get too far in depth because I know Dr. Barker will be talking about short span economy next week. So I'll leave that to his presentation. And with that, I'm going to get into my introduction. Before I do, I was looking at chat. There's a few folks that seem to be having some issues with sound. I'll mention that. I don't know if there's anything in chat that AGA can respond to, but I'm just going to go ahead and keep on trucking and get into the presentation. So first, I want to talk about the Short Span Steel Bridge Alliance and make sure that everybody is aware of our background and our history. So we've been around for a good little while. The program officially started in September of 2007. And so it's the Short Span Steel Bridge Alliance. I'm sure you could guess what the objective is. You know, we want to make steel the material of choice for short span steel bridges. Really what we want to try and do is provide owners and designers and what have you another option to consider when working on a short span bridge project. Another aspect of the Short Span Steel Bridge Alliance, which is what I think makes it really special, is that it's not just a couple of fabricators or university professors or whatnot getting together and saying, well, this is how you should be doing it. The members within the Short Span Steel Bridge Alliance, the way I like to describe it is it basically corresponds to every cog within the bridge delivery engine. You have steel producers and service centers. You have folks that manufacture fasteners, coaters. You have design firms, trade organizations, universities. So when the Short Span Steel Bridge Alliance, when we've, a lot of these work products that we've put together have really been the industry as a whole coming together and developing these solutions and defining what's efficient and economical for short span steel bridges. And so I think that's a really important aspect that should be brought up. I want to draw everybody's attention to the website. It's shortspansteelbridges.org. You can also find that with just a quick Google search. If you just Google short span steel bridges, it's the first link that pops up. You'll find a link to eSPAN140, which is going to be a primary focus of my talk today. You'll also find links to the Bridge Technology Center, which I'll get into a little bit more near the end, as well as a wide variety of technical design resources, case studies. You'll find news updates and links to all our social media accounts and whatnot. And if anybody out there is interested in joining the Short Span Steel Bridge Alliance, I would contact Dan Snyder. He's the director of the SSSBA. His email address is dsnyder@steel.org, and you can see his phone number here. We'd love to have you join the team. And so with that, I want to get into really the why it was that the Short Span Steel Bridge Alliance was formed. And it really just comes from an observation of the short span bridge market. If you look at short span bridges in the United States, you find that the vast majority of them have gone traditionally towards concrete solutions, things like precast or pre-stressed solutions or adjacent boxes or things of that nature. And so there's a gap in that market share. And this webinar is just one of a number of presentations that myself and other members of the Short Span Steel Bridge Alliance have made. We've traveled across the country making presentations to thousands of engineers, from designers and consultants to county engineers and owners and what have you. And what we found is that a lot of times the counties and the DOTs and whatnot just really aren't familiar with short span steel bridge design, just because of that gap in market share. There's sometimes depending upon the state, there can be a lack of standard solutions with the state agency and whatnot. And there's also two other perceptions, if you will, that hopefully today will begin to be broken down a bit. One is that steel bridges are always perceived to be complex. Like they're all unique Swiss watches and whatnot. And the other is that they're too expensive. And hopefully after today's presentation, you'll see that those preconceptions aren't always the case, particularly when you're talking about efficient short span steel bridge solutions. What we've done within the Short Span Steel Bridge Alliance is try and develop a series of standardized designs for short span steel bridges. And this is one of a number of projects that we've engaged in within the Alliance. And so the Bridge Technology Center, of which I'm one of the members, we led a 3-year wide effort, again, involving the owners, the fabricators, designers, service centers, et cetera, to try and develop the most efficient and economical standard designs that we can for bridges in the short span range. And so we looked at a wide net of solutions, and from that selected the ones that are the most economical. And I'll get into that process later on. And we've also developed an online tool for you as a user to access those standards, and that's eSPAN140. Now, these standards and eSPAN140 are free and available for anybody to use. The Bridge Technology Center has also been working with states to adopt state-specific standards, and I'll talk about that specifically in the end. But with that, I think we provided a little bit of context with what we're talking about today, and I'd like to get into the standards themselves. I want to talk about our goals with developing the standards, talk about some of the design parameters for the bridge engineer folks in the room, all the code provisions that we adopted, and then we'll get into some weight comparisons and some of the decisions that we made when implementing these standards. So let's talk about the standard designs and what our goals were and how we went about this. So obviously we've been trying to develop the most efficient and economical short span steel bridge solutions that we can. So, our goal was to develop a set of standards that were economically competitive. We wanted to try and make the design process for a county engineer or a consultant or what have you. We want to try to make that design process as streamlined as we can. We also made it a point when we developed the standards to make sure that our details that we chose were as simple and repetitive as possible. We wanted the member sizes and the plate selections to be as straightforward as possible. Again, the goal was to keep it simple, keep it efficient, keep it economical. Now, in terms of what we developed, so what we did is we took bridges in the short span range, which we define short spans as any span that's less than or equal to 140 feet. We took those span lengths and we divided them in 5-foot increments. So we started at 40 feet and we designed girders at 40 foot long and 45 foot long, 50, 55, 60, so on and so forth. And so for each of those different span lengths, we designed a particular girder. Most state standards have details very similar to that for steel or even concrete solutions. And so for each of those different span lengths, we have a unique design. And so the idea is, okay, well, let's say you're designing a bridge that's, 72 feet long. And so when you would input 72 feet into eSpan, which I'll talk about later, what eSpan will do is round that up to the next increment, and it will report the solution for the 75 foot bridge. The idea is that if you have a girder that will work for a 75-foot span, it will certainly work for a 72-foot span. Now, another thing that we did during the initial development is we looked at girder spacing. A lot of the standard solutions and standard designs that are out there, a lot of times they're based on a unique cross section. So you have a bridge cross section, and here are some girders, and then you have another bridge cross section, and then here's some girders, and that's fine as long as your cross section matches the one that the standards were developed off of. If the If your bridge utilizes, let's say, a different girder spacing or some of the parameters are different, then that set of standards might not apply to you. What we decided to do was instead look at it just from a girder spacing approach. So we designed girders for 4 different increments of girder spacing. We looked at 6 foot, 7 foot 6 inches, 9 foot, and 10 foot 6 inches. And again, similar idea. If you have a girder spacing in your cross section that's, I don't know, 8'2", eSPAN would then round up to the next increment and report the solution for a 9-foot girder spacing. Again, the idea is if you have a girder that would work for a 9-foot girder spacing, it'll certainly work for 8'2". And so for each of those permutations, so each of those increments of span length and for girder spacing, we did a full-blown design of a short span steel bridge. So that included the design of the girders and looking at cambers and what have you. We laid out the shear studs, laid out the stiffeners if needed. We provide all of the welding details, the fabrication details. For each of those options, we have an elastomeric bearing that's designed. We have a sample concrete deck design reinforcement laid out. The idea is to provide you as the owner or the consultant with as much information as you can to begin that process. See, the primary value in these standards is really to use as an estimating tool. So now the idea is that with eSPAN and with these standards, you have the ability to produce a valid design in a few minutes. As you'll see when we start getting into eSPAN, if you all created an account in eSPAN right now, you could probably have a bridge design before I'm finished with my presentation. It's that fast. And so the idea is you can obtain that initial preliminary design in minutes, and then you could contact a fabricator and get a cost estimate within a day or maybe even less. And so the idea is, okay, now I have an idea of how much a steel solution is. I could compare that with a concrete alternative. And if that steel solution is going to be faster and cheaper, maybe it's something that you ought to consider. Again, with all bridges are unique, and there might be some tweaking that needs to be done within an individual design, but the idea is that it will get you started and get you 90% of the way there in that design process. Now, for each of those increments, increments of span length and girder spacing, we designed 4 different individual girders. And we did that because we wanted to make sure, and this will make sense here in a little bit, we wanted to make sure that we were providing the right solution for the right span range. And you'll see later how we made those decisions. So for each of those increments, we looked at 2 different plate girder options. One, just a homogeneous plate girder with 50 KSI steel throughout. And we also included a hybrid option that had a 70 KSI bottom flange. So 2 plate girder options and then 2 rolled beam options. So with the rolled beams, we adopted 2 philosophies. So one of them is what we're calling a lightest weight option. So literally just looking at a given increment of span length and girder spacing and literally trying to find the lightest section out of the steel manual that we can to safely resist those load demands. And then the other philosophy we used was limited depth. And so that one we tried to achieve a target L/D ratio of 25. So those girders are a little bit heavier, but they're a little bit shallower. So if you have hydraulic opening issues or clearance requirements, it might be something to consider that you might want to look at those options. And another point worth mentioning is that when you look at the various details and output from eSPAN, you won't find any, 15, 30 seconds inch plate or any dimensions that utilize, odd plate thicknesses, I guess you would say. We designed the girders to accommodate commonly stockpiled plate thicknesses. So things like 1/2 inch, 3/4 inch, stuff that the mills are rolling all day, every day, as well as commonly available rolled shapes as well. So again, we're trying to make sure that the solutions that we provide are efficient, economical, and readily available for you as the user. Now this slide is for the bridge engineer junkies in the attendee list. So we designed the bridges according to AASHTO LRFD. So we assessed specifically, we looked at the strength 1 limit states, service 2. We designed for fatigue. Looked at constructability. We assumed a single continuous deck pour for our deck casting sequence, and we also looked at an L/800 live load deflection limit. For our live load, we had utilized the HL93 vehicular live loading that's present in AASHTO. We also have our additional design loads here listed. So, for instance, we utilized a stay-in-place unit weight of 15 pounds per square foot. We utilized a future wearing surface of 25 pounds per square foot. For our end barriers, we utilized concrete jersey barriers, and we used 520 pounds per foot for the weight of each of those barriers. We computed the weight of the girder and then added an extra 5% to account for miscellaneous details, bolts and plates and whatnot. We utilized 4 KSI concrete for the deck, 150 pounds per cubic foot on the weight of that, and then 490 for the steel. We used a 2-inch haunch for the girders where appropriate. And then for our plate girders, when appropriate, we include a flange transition. Our rule of thumb is that we only included a flange transition if we would save about 1,000 pounds of steel for a given solution. But when we did transitions, we ensured that we maintained a constant flange width and a constant web height to streamline the fabrication process of those girders. Now, so like I said, for each one of those span lengths and each one of those girder spacing options, we did a unique design of 4 different girders, 2 plate girders and 2 rolled beams. Now I'm going to grab my pointer here. Use the pointer here. So you should see my mouse pointer here on the screen. I want to show you some weight comparisons that we made once the designs were completed, because we wanted to make sure that when we recommended the designs to you as the user, we wanted to make sure that those designs were reasonable and that we were making common sense recommendations. So on the x-axis on this plot, I have the span length, and then on the y-axis, I have the weight of the girder. So on the x-axis, so first off, I think it would make sense that as the span length increases, the girder weights are going to increase, because not only are the girders getting longer, but they're getting deeper and heavier as the span length increases. So I think that makes sense that it trails upward and kind of goes up in a nonlinear fashion. But I want to look at the comparison between the different options. Okay. Now, these 2 curves that you see my mouse trailing right here, this green curve and this purple curve, the one with the triangles and the X's, those are the ones that correspond to the rolled shapes, the W sections that you would normally use. Whereas these 2 options here correspond to the plate girders. Now, what happens is, there's only so many shapes in the manual that you can use to, design a given bridge. So what happens is, once you get past it's like around 100 feet, the rolled beam weights just sort of shoot through the roof. I mean, look at the weight comparisons between, if we're looking at this 140-foot girder, look at the weight comparisons between the rolled beams and the plate girders. The plate girders are substantially lighter. So if I was recommending solutions to an engineer, if they told me they had a 130-foot long bridge, I would tell them to use a plate girder, because you're going to get significant weight savings with a plate girder as opposed to a rolled beam. So when you run eSPAN, if you have a bridge that's over 100-foot long, it will not report a rolled beam solution, because it's not the most economical choice for that range. Now, on the flip side, let's look down here. Let's look at the lower span ranges, like the 40, 45, 50 foot girders. Down here, the girder weights are pretty much all the same. I mean, there's, the reason for using a plate girder is that you can tailor the size of that girder, the thickness of your flanges and the depth of your girder and all that. You can tailor those dimensions to your load demand, so you can tweak it to get the most economy that you can. But that effect is far less pronounced when you're talking about these lower span ranges. So if I was designing a 40-foot bridge, I probably wouldn't bother with a plate girder. I would just go with a rolled shape. So sort of similar to the long span inputs. If you input a span in eSpan that's really short, so if you input, let's say, a 40-foot long bridge, eSpan will not report a plate girder solution. It's only going to report a rolled beam, because in these lower spans, there's really no point in going with a plate girder. You might as well just go with a rolled beam, because you're not going to get any significant weight savings, and it's all about the overall economy. So based on the weight comparisons of the resulting designs, so when you run eSpan, and you'll see this when you first open a given project, these are the span ranges that eSpan uses to report a given solution. So if you input a span anywhere from 40 foot to 100 foot, eSpan will report a rolled beam solution. If you input a span anywhere from 60 to 140, it will report a plate girder. The hybrid girders, we didn't notice any significant economy in the 80-foot span ranges. So eSpan will only report an option on the hybrid girders at 80 foot or higher. All right. So that's into the development of the standards. What I want to do now is I want to go through eSPAN140, which eSPAN140 is how you as the user would access these standards. And I want to go through that process by which you would obtain a solution. I think you'll see it's very, very easy and quick to do. So first off, let's talk about what eSpan is. So I'm sure that some of you are probably thinking about these standards, and you're thinking, okay, there's 4 different girders for 4 different girder spacings for 20 some different increments of span length. And so for each of those, increments, there's all sorts of data. There's plate sizes, and cambers, and stud layouts, and bearing sizes. That's a lot of data. And there's a couple of ways that we could make that data available to you as the user. Well, one way is to just put it on a bunch of standard detail sheets and print it out. And so if you do that and you combine all of this into one particular document, it gets to be kind of big, and it's a lot of information all at once. Instead, what we've done is we've developed a user interface for you to access the standards, and that's eSpan140. So the first sort of misconception I want to make sure that I break through is that eSpan140 is not a design package. It's not a software program that you could use to design a girder. It doesn't really work the same as something like LRFD Simon or maybe MDX or something like that. Instead, eSpan140 is really just a user-friendly lookup tool. The idea is that you would input the parameters associated with your specific project, and then eSpan will intelligently search the standards and find the solution that's appropriate for your bridge and report that to you as a PDF, a custom PDF solutions book. And so the standard designs that are available within eSpan are obviously the rolled beam and the plate girder bridges that I've discussed previously, as well as solutions for buried soil steel bridge structures. You'll also find information for manufacturer prefabricated solutions, as well as information on coding and a wide library of industry context to help you implement your short span steel bridge project. Again, a couple other points that I want to mention before we get into this. It is very, very easy to use. I'd argue you really don't even need to be an engineer to utilize eSpan. If you understand some basic properties of your bridge, when I say basic, I mean how long is it? Does the bridge have sidewalks? If you understand that basic information, you can generate a bridge design. Another thing is that eSpan is complimentary. It's free to use. So I urge everybody in here to get started on eSpan. Again, like I said, by the time I'm done with my presentation, you can already have a design underway. Let's get into an example project in eSpan just to show you how this works. So as soon as you create an account within eSpan, and if you can create a Facebook account or something, you can do this. It's not that difficult. You'll see a button that says Start New Project. You click that. and then you'll see the following dialog boxes. So let's say we're designing a sample bridge in Morgantown, West Virginia. It's on Main Street, or it's carrying traffic across Main Street. And then we'll say this bridge is 82 feet 4 inches long. And so a couple points. So when you put 82 feet 4 inches, what eSPAN will do is round that up to 85 feet, and it will report the girder solution for an 85-foot span. And again, the idea is if it'll work for that span, it'll work for 82 foot 4. The other point worth mentioning is if you're ever in doubt about what a specific parameter means, for instance, when you start to enter the 82 foot 4 span, there'll be a highlight on this image here on the right that'll show you specifically, okay, here's what we're talking about. This is the dimension that we want to help guide you as the user to make sure that you're providing the appropriate input. Next, you get into the project details, and this is we've got some general dimensions that it's asking for. So we'll say this bridge has 2 traffic lanes. It has a clear roadway width of 30 foot. We'll say that it has 2 parapets or barriers that are 15 inches wide, so 1 foot 3 inches. And the deck overhangs are, we'll say, 3 foot 0 inches. You can also specify if you would like to incorporate sidewalks. You can say if there's 1 or 2 sidewalks and how wide they are. I'm not going to use one for this input, but I just wanted to show you that you can specify that. Last thing is that you would enter your skew angle, your ADT, and your design speed. The ADT and the design speed really won't affect the roll beam and plate girder solutions, but it can affect other solutions within eSPAN. And then that's really it. Once you generate that, once you input all of that information, you click generate, and then it cranks away, takes about 30 seconds, and it will generate a customized PDF solution for your given project. So based on the inputs that I just generated, eSPAN searched the standard designs and found that a potential plate girder solution would be a homogeneous plate girder with a 14 by 3/4 inch top flange, a 32 by 1/2 inch web, and a bottom flange that is 14 inches wide and transitions from 1 inch thick at the end to 2 inches thick at midspan. And you can see the shear stud layout, the diaphragm spacing, and as well as the individual girder weight. It also provides roll beam solutions, but I've cut some of this out just for the interest of time, just to make sure that we can get through some of the various topics. But again, I urge everybody to try this out. You'll see typical fabrication details that are provided. This is looking at the girder elevation and the stiffener details and the sizes associated. We've got also different fabrication details associated with channel diaphragms. We have a sample reinforcement pattern for a reinforced concrete deck, as well as the cross-section stud detail that you see there in the top right. We have bearing details. So again, there's a bearing pad for each solution. So you can see the size of the bearing pad as well as the number of internal layers required. There's also a series of pages that you'll see towards buried bridge solutions and the various options and sizes associated with that, as well as a series of prefabricated manufacturer solutions that might work for your given project, as well as industry contacts for you to be able to implement this option, or at the very least to contact them and get a rough cost estimate. Again, so you can compare that against the traditional concrete alternative to see where you're at from an economic perspective. There's also information on the durability solutions. Again, our 3 durability solutions looking at weathering steel, painted steel, or steel that's been galvanized. We'll have a presentation later in the series specifically focused on hot dip galvanizing that I highly recommend you all check out. Now, I don't want to steal Dr. Barker's thunder too much. Next week, he's going to be talking specifically about steel bridge economy, and that's going to be a great presentation. I highly recommend that you all check that out. But I do want to lightly touch on the economy and the economic aspects of this process, because like I said earlier on in the presentation, we've given presentations on this topic, for years across the country. And we always get that one question that's, yeah, that's great, but how much is it? Or, yeah, it's great, but it doesn't matter because steel bridges are always more expensive. And so I want to just briefly highlight a couple of case studies, just so that everybody gets an idea of the economics. I'm going to be focusing on Audrain County, Missouri, and you'll see why here in a second. We had a county engineer out there that worked with us and provided us some of the economic data on a couple of candidate projects. I want to show you, these are a couple projects that were built in 2012 in Audrain County, Missouri. If you look at these two bridges, they're pretty much identical, except for the fact that one is steel and one is concrete. They have the same roadway width, the same structural depth, virtually the same span, plus or minus a couple of feet. Just one utilized a steel superstructure and one utilized a concrete superstructure. And when you look at the be-all, end-all cost of the superstructure in a cost per square foot fashion, what you find is that the steel bridge came in at about $37 or $37.50 a square foot versus the concrete bridge, which came out at $50.60 per square foot. Now, a couple things about that. First off, this is not bid prices. This is what was paid at the end of the day when the bridges were complete. This was what was paid by the owner for these bridges. And again, same work crew, same guardrail system, same roadway width, same structural depth, but one went steel, one went concrete, and the steel bridge came in at almost quarter cheaper, if not more. I skipped a lot of details on this, and I think that Dr. Barker might talk about this in his presentation next week. I highly recommend that you check that out. Again, I didn't want to steal his thunder because I wanted to make sure that he had something to present about as well. Now, another final point I'll mention on the Audrain County data. I'm sure some of you are like, great, you found that one bridge where it was cheaper. This is looking at a little bit of a wider cross-section in that same county. And what you find is steel bridges don't always come in as the cheapest solution. For instance, if you look at some of these bridges, you have some steel bridges that came in at like $102 a square foot versus, here, let me use my pointer here to sort of highlight what I'm talking about. So if you see here, for instance, we have some steel bridges that came out as $102 a square foot versus some concrete solutions that came out at $91. But the big point to keep in mind is that steel bridges are competitive. I mean, on average, the steel bridges came out cheaper. And again, same work crew, and a lot of these scenarios are very, very similar. Again, we just want to make sure that you all, as owners and designers and consultants, are considering this as an option. We also wanted to make sure that eSPAN stood the test, that these girders would actually work in direct application. So we worked with a county engineer in Buchanan County, Iowa. This was the first direct application. The county engineer, we ran eSPAN for this given bridge. eSPAN suggested W36 by 135 sections for the girders, and that's what he built. And so you can see the image on the left. This was the bridge before, and the image on the right, that was the bridge after. And so this was actually taking the eSPAN and directly applying it to show that these girders do meet the standard. There's also a couple other cases I want to mention. This was the first. This is the High Point Lane Bridge in Boone County, Missouri. The county didn't know that the steel could reach these spans, and so this is one of these instances where eSPAN was utilized to develop a design, and that design ended up winning the project. Same thing with this KDOT Shawnee County Bridge that's 112 foot long. That they initially assumed that concrete would be cheaper, but they ran eSPAN. eSPAN produced a valid option, again, within minutes. And it ended up getting them a lower cost estimate, and they won the job. So again, the proof's in the pudding here that steel bridges are economically competitive and a serious option for short span situations. I want to mention some final remarks just on some various work efforts, as well as some logistical items. One of the things I mentioned earlier was that the Bridge Technology Center has been engaged in efforts to sort of generate eSPAN-based standards that would be state specific. And our recent efforts have been focused in the state of Ohio. The folks in Ohio have been very receptive to developing state-specific standard solutions, and we're currently in the process where it's sort of in the review phase. So we've produced drafts, and it's in that back and forth review phase. But the idea is that these would be standards that would be applicable for that state. We're eager to assist other agencies in the development of these owner-specific standards. So if there's anybody out there that's interested, I would urge you to either contact Dan Snyder or myself or some of the other folks within the Bridge Technology Center, and we'd be more than happy to work with you to make that a reality. Speaking of the Bridge Technology Center, so these are free resource. I mean, we're a free resource available to you as owners and designers, and you can find our contact information available on the website. I'd highly recommend that you contact us if you ever have any questions about this or any of the solutions that we've developed within SSSBA. We're here to help. Again, that's what we're here for. We obviously provide training and education. We're doing that today, but hopefully when things go back to normal, we can start to have a little bit more of an in-person experience. I mean, like I said, we go across the country and do this stuff. I mean, we've done half-day workshops, with county engineers, things like LTAPs and whatnot. We obviously do webinars and whatnot. We'll do steel bridge forums and what have you. And so we're more than willing to come out and educate engineers on these various topics. Again, I would urge you to contact Dan Snyder with SSSBA, just dsnyder@steel.org. I'd also urge you to check out our social media profiles. I have the links here for Facebook and for Twitter. And so, again, we'd love to have you join our efforts. We'd love to have you learn more about what it is that we do within SSSBA. Want to finally mention next week's webinar. So again, I mentioned this a little bit earlier, but just to make sure everybody's clear, next week's webinar will be on short span bridge economy and life cycle costs. It'll be presented by Dr. Michael Barker at the University of Wyoming. It'll be next week, same time, same channel, Tuesday at 3 p.m. I would highly recommend that you check it out. It's going to be a great presentation. With that, I want to thank everybody. I've noticed that there's been a lot of activity here. I hope it hasn't diverted me too much, but I know we've had a lot of really good feedback in there. I really want to thank everybody for attending. If there's any questions that I can answer audibly, I'd be happy to. And with that, I'll turn it over to AGA. Again, thanks everybody for attending.